Hello dear students, this is grade 11 mathematics lesson on unit 6 matrix and determinants. So today we focus on inverse of square matrix and Cramer's rule. So after revising this lesson, you are expected to determine inverse of a square matrix and apply Cramer's rule to solve system of linear equations. So now let's proceed to the lesson. A square matrix A is said to be invertible or non-singular if and only if there is a square matrix B such that the product of A times B and B times A gives you identity matrix. Where this identity matrix has the same order as A. The size of this identity matrix is the same as matrix A. And the inverse of a matrix, if it exists, it is unique. The inverse of a matrix is this. If it exists, it's unique. And we can evaluate inverse of a square matrix if you can evaluate inverse of a matrix if a matrix is only a square matrix. That means only square matrix can have an inverse. Now the inverse of a matrix A, is whenever it exists, it is denoted by this one. It is A power of minus 1. So we can read it as A inverse. You have to note this: A and A inverse have the same order. They have the same size. A matrix that does not have inverse is called singular matrix. If it doesn't have an inverse, we call this singular matrix. Okay. Now let's see this example. Here it says that show that these two matrices are inverse of each other. To check this, if this one, assume this matrix A is this B, if this one is the inverse of this one, then the product of these two matrices must give us identity matrix of order this one, 2 by 2. So let's check this one. Solution. Take this one, the first matrix, 3, 1, 5, 2, times the other one, 2, minus 1, minus 5, and 3. So we multiply this row by column. So this first row multiplies the column, and therefore you have this one. 3 multiplies 2, it is 6. And this 1 multiplies negative 5, it is minus 5. And second, this row multiplies the second column. 3 multiplies negative 3, it is negative 3. And this 1 multiplies 3, you will have positive 3. Here, this one multiplies this row, the second row multiplies this column, therefore 5 times 2 it is 10, and 2 times negative 5 is this negative 10, and the product of this also 5 times negative 1 is this negative 5, 2 times 3 is this positive 6. Therefore, when you add this, you get this result. 6 minus 5 is it is 1, minus 3 plus 3 it is 0, and this one is also it is 0, and the sum of these two it is 1. Therefore, as you can see, the product of the two gives you an identity matrix of order 2 by 2, which is equal to the order of the given matrix. Not only this one, even you can check this. You can multiply by changing these two. So 2 minus 5 and minus 1 3 times second matrix 3 5 3 5 1 2 3 5 1 2. By the way, you can multiply these two. When you multiply, you can check by yourself. When you multiply these two, you get the same result, 1 0 0 1. Since the product of these two matrices in the given order, the first times the second or second times the first, gives you identity matrix, an identity matrix. So one of the matrices is the inverse of the other. So this is it. Therefore 3 5 3 5 1 2 1 2 and 3 5 1 2 and 2 minus 1 2 minus 1 minus 5 3. These are inverse to each other, they are inverse to each other. So this is it. Now let's continue to the other part. So this is how we did the question. So they are inverse to each other. Now let's continue to how to find the inverse of invertible matrix using adjoint. The adjoint of a square matrix A is this defined as the transpose of matrix C, where this matrix C is a matrix of cofactors of the given matrix. Therefore, C is or Cij is a matrix of cofactors of the element Aij, and adjoint of matrix A is denoted by this one. It is denoted by adjoint of A, and it is given by adjoint of A is equal to the transpose of the matrix of cofactors. So adjoint of A is given by this form. Now, a square matrix A is invertible or non-singular if and only if the determinant of A is different from 0. If A is invertible, then A inverse is given by this equation. The inverse of the matrix will be given by this formula. It is A inverse is equal to adjoint of A divided by determinant of A. So this how is a formula to evaluate inverse of a given matrix. Now let's continue to example. Here we are asked to find the inverse of matrix A, where matrix A is given to be it is 2 1 0 1 1 4 minus 3 2 5. To find the inverse of this matrix, we need to find, you know this, how to inverse. The formula is equal to this adjoint of matrix A divided by determinant of the determinant of A. This is a formula. Therefore, we need to find adjoint of matrix A and its determinant. So let's see this together. Now, to find the adjoint, we need to find the cofactors of each entry, the cofactors of each entry. So that will give us the cofactor matrix. So let's find that. Therefore here C11, this part, you cancel these two, you get this, the determinant of 1, 2, 4, 5. 1, 2, 4, 5, negative 1, the power of 1 plus 1. It gives you negative 3. And the cofactor of 2, 1, 2, or it's the cofactor of this number is simply delete this column and in this row you get 1, negative 3, and 4, 5. This result. So, and negative 1 times negative 1 the power of 1 plus 2. So, this gives you negative 17. And next, we need to find the other cofactor of the row. The cofactor of the row, cancel this column and in this row, you have this one, 1, negative 3, 1, negative 3, 1, 2. So, to find the minor, by the way, you can put this sign. This part is plus, minus, plus, minus, this one, plus, minus, plus, minus, plus. We can use this to find its cofactor or to find the sign of this one. Therefore, the cofactor of 1, 3, 1, 3 is this number, it is plus, it is positive, this one is positive, and we cancel row and column and you get 1, negative 3, and 1, 2. And the determinant of this gives you this 5. And you continue for each entry like this. So the next entry is 1, 1. So the cofactor of 1, it is minus here. Cancel these two, you get 1, 2, 0, 5. The result gives you negative 5. And then the cofactor of the next number 1, the sign is plus, it gives you plus. And cancel these two, you get 2, 3, 0, 5. 2, negative 3, I mean, and 0, 5. So for this entry 4, 4, the sign is it is minus. This one is minus. This one is minus. And cancelling its 0 and column that 4 belongs. The remaining part will be 2, minus 3, and 1, 2. 2, minus 3, and 1, 2. And the result you get minus 7, 4, C2, 3. C2, 3. And you continue. Let's find the cofactor of negative 3. Minus sign, you put minus sign, this one it is plus, because 3 plus 1 is it is 4, negative 1, the power of 4 is positive, so plus. So when you cancel this row and column, you get 1, 1, 0, 4. 1, 1, 0, 4. So this result gives you this 4. And C3 to this number, the sign it is minus. And when you cancel the row and column that 2 belongs, you get 2, 1, and 0, 4. 2, 1, 0, 4. Therefore, the determinant of this value together with this one gives you minus 8. And the next one, 5. So the sign is it is plus. When you delete 0 and column, the 5 belongs, you get 2, 1, and 1, 1. 2, 1, 1, 1. So this result gives you 1. Therefore, we have found the cofactor of each entry. And we have found the cofactor matrix. So the cofactor matrix, minus 3, minus 5, 4, 17, 10, and minus 8, and 5, minus 7, and 1. 5, minus 7, and 1. So this the transpose of this cofactor matrix, the transpose of this cofactor matrix gives you this, the adjoint. Therefore, the adjoint of this matrix A given by T is taking the transpose, minus 3, minus 17, 5. This row written in column 4, minus 3, minus 17, 5. You write in this form, minus 5, 10, minus 7, column 4, minus 5, 10, minus 7, 4, minus 8, 1, 4, 4, negative 8, 1, 4, negative 8, 1. So, this is the adjoint of the given matrix A. Then, what remains is, the adjoint is we found this one, the adjoint, and the cofactor matrix is we have found this one, and matrix A is given. So what remains is the determinant of A. The determinant of A is given by selecting any row or column and multiplying that by its cofactor. For our case, I select the first row. Our matrix A is here, and the cofactor of this matrix A is here. Therefore, the cofactor of 2 here, it's negative 3. The cofactor of 1, minus 17. The cofactor of 0 is 5. Therefore, multiplying this, you get the determinant. Determinant of A equal to 2 times negative 3 plus 1 times negative 17 plus 0 times 5. You get negative 23. By the way, you can use any row or column to determine the determinant of that matrix. So, now, next to this, what remains here is finding or calculating A inverse. To calculate A inverse equal to adjoint of A over determinant of A, or 1 over determinant of A times adjoint of A. So, this equal to, we have found determinant of A. The determinant of A is this negative 23. Therefore, 1 over negative 23. It means that negative 1 over 23 times adjoint of A. We have found the adjoint of matrix A, this number. So, this is the result. So, multiplying this matrix by negative 1 over 23, you get the result. Negative 1 over 23 times negative 3, it is 3 over 23. The product of negative 1 over 23 and negative 5, it is 5 over 23. The product of negative 1 over 23 times 4, it is negative 4 over 23, and so on. So, therefore, the inverse of matrix A is equal to, it is this result. This is how we evaluate inverse of a matrix. Now, let's continue to the other part. Now, the next concept is Cramer's rule. Cramer's rule in solving system of linear equation. Now, determinants can be used to solve. We use determinants to solve system of linear equations with equal number of equations with unknown variables, with unknowns. So, now let's see how to apply the Cramer's rule. Now, let's take this system of equation is given a1x plus b1y plus c1z is equal to d. In the second equation, a2x plus b2y plus c2z is equal to e, and a3x plus b3y plus c3z is equal to f. This system of equation has exactly one solution provided that the determinant of the coefficient matrix is different from 0 or non-zero, which means that the determinant of coefficient matrix means this A1, I can write here A1, next A2, A3, here B1, B2, B3, and C1, C2, C3. This is a coefficient matrix for this system of linear equation. If the determinant of this coefficient matrix is non-zero, implies that the system of equation has exactly one solution, and we can calculate the solution using this form. Okay, so to find or to solve the value of x, you use this formula. X equal to is dx over d, and y is equal to is dy over d, and z is equal to, it is dz over d. D means it is the determinant of coefficient matrix. The coefficient matrix here, it is A1, A2, A3, B1, B2, B3, C1, C2, C3. The determinant of the coefficient matrix is D. It is for all, the denominator is D. Therefore, D is the determinant of the coefficient matrix. And dx is simply, it is the coefficient matrix a little bit modified. How? Dx simply, you change the coefficient of x by the solution, by this one. So therefore here you will have what? The coefficient matrix will be for dx will be this D, E, F, B1, B2, B3, C1, C2, C3. Therefore, dx is equal to this, the determinant of DEF, B1, B2, B3, C1, C2, C3. The determinant of this gives you dx. Similarly, dy is also, it's a coefficient matrix a little bit modified. The determinant of coefficient matrix by changing the coefficient of y by this one. Therefore, dy is equal to this a1, a2, a3. This is changed by the solution def and then c1, c2, c3. So the determinant of this is this dy. And z is equal to this dz over d. The determinant of the coefficient matrix of z is simply you need to change the coefficient of matrix of this part by the solution. Therefore, dz is equal to simply a1, a2, a3, b1, b2, b3, but this is changed by the solution. Therefore, here dz is equal to a1, a2, a3, b1, b2, b3. This part is changed by df. Therefore, z is equal to the determinant of z coefficient matrix over the coefficient matrix will be give us the value of z. Therefore, this is a formula to evaluate system of equations using Cramer's rule. Now let's see example for this. By the way, you can use for 3 or more equations to solve system of equation using Cramer's rule. For our purpose, let's use this one as an example to solve this. Solution x is equal to it is dx divided by d. Therefore, this equal to dx means it's a coefficient matrix by changing the coefficient of x. Therefore, it is a determinant of this part will be changed by 2, 3. Here 2, 3 and negative 4, 7 divided by the determinant of coefficient matrix is this one 3, 7, negative 4, 7. The determinant of 3, negative 4 and 7, 7. So this equal to 7 times 2, it is 14 minus 3 times negative 4 is this negative 12. So this becomes plus 12 divided by this result it is 7 times 3 is this 21 minus 28. 7 times negative 4 is negative 28. So minus becomes this plus 28. Therefore, this equal to 14 plus 12 is 26 divided by 21 plus 28 is this 49. So this is the value of x. And let's try to evaluate the value of y. Y is equal to simply it is dy divided by d. So this equal to dy is simply a coefficient matrix by changing the coefficient of y by the solution by this number. Therefore, this equal to is the determinant of 3, 7 and this part is changed by the solution to 3 divided by the coefficient matrix, determinant of coefficient matrix. Since d we have found here it's 49, no need of doing again. So this equal to this result will be it is 3 times 3 it is 9 minus 7 times 2 it is 14 divided by the determinant of the coefficient matrix, it is 49. So this equal to 9 minus 14. This equal to, it is negative 5 divided by 49. So this will be, it is the final answer. So this how to apply the Cramer's rule. Okay, so therefore the solution set is this: x is this 26 over 49 and y is this negative 5 over 49. So to summarize, what we have seen today is the first concept that we have seen today is about the inverse. A square matrix A is invertible if and only if its determinant is different from 0. And if A has inverse, or if A is invertible, then the inverse of A is given by this formula. It is adjoint of A over determinant of A. And if we have such system of equation, to solve this using Cramer's rule, what you do is x is equal to this dx over d, where dx is this coefficient matrix where the coefficient of x is changed by the solution, and y is also, it is dy by d, where d is, it is the determinant of coefficient matrix, and dy is, it is the determinant of coefficient matrix where the coefficient of y is changed by the solution. And z is equal to this dz over d, which is equal to d is this the determinant of coefficient matrix, and dz is the determinant of a coefficient matrix where the coefficient of z is changed by the solution. So this is the formula to solve system of equations applying Cramer's rule. So these are all about today's lesson. So for you to try, I will give you exercise. Please try this question: find the inverse of this matrix and solve this system of linear equation using Cramer's rule. So this is all about today's lesson. Until next class, goodbye.